Welcome everybody to One World Mathematical Game Theory Seminar. Today we're happy to have with us Wang. He did his PhD in the economic departments at Stony Brook University, then came to do a postdoc in Tel Aviv University, School of Mathematical Sciences. He's currently an assistant professor at Nanjing Audit University, and he's continuing his work with Ehud Lehrer, the cooperation with Ehud Lehrer. They have work about values of information, and today he will present to us work about stochastic dominance and subjective option valuations. Tao, the stage is yours.
Yeah, thanks Galit for introducing me, and thanks everyone for coming to my talk. So it is my pleasure to present this joint work with Ehud Lehrer here. As we know that when decision makers face the dynamic decision problems under uncertainty, very often we see that different decision makers, they hold different prior beliefs about the same unknown state of nature. This may due to, for instance, the difference in their past experience or knowledge, or simply because they have different personalities. And some people tend to be more optimistic, while others tend to be more pessimistic. So this is reflected in the difference in their prior belief about the same unknown state of nature. So what we do in this paper is the following. So our objective is to investigate the implications of several well-known stochastic dominance relations among prior beliefs in the so-called binomial tree model, including we discuss the following stochastic dominance orders, including first order stochastic dominance, hazard rate dominance, and the reverse hazard rate dominance, and the likelihood ratio dominance. Okay, notice that these stochastic dominance relations are related to the location or magnitude of a random variables. As a result, we do not discuss those stochastic dominance relations related to dispersion or the variation of random variables, such as the second and the third degree stochastic dominance. Okay, so in particular, we establish connections among the following conditions. First, the stochastic dominance relation among prior beliefs. And second, we look at the stochastic dominance relations among posteriors conditional on certain histories. And third, we examine the stochastic dominance relation of probability distributions over certain histories. Because you know that different histories may lead to different payoff. So therefore, by looking at the probability distribution over a certain set of histories, we can calculate and compare the values of different prior beliefs. Okay, and as an application, we'll examine the implication of subjective valuation of options, including the European and the American options. We'll talk to that later. But let me first start with the so-called tree model or binomial model. It is actually very simple. So each period, a decision maker observes a random outcome, either U or D. You can think of U as up or D as down. And the probability that an U outcome is observed each period is given by P. Okay, so P is unknown to the decision maker. And the decision maker holds a prior belief about P. You can think about U or D as increase or decrease in a firm's sales or profit. And the P can be interpreted as the performance of a firm. Okay, and also in you can imagine in setup of online rating, U or D may refer to thumbs up or thumbs down, and P is a parameter that reflects how satisfied a consumer will be from purchasing from some online store. Okay, so here notice that the observations in different periods are independent, conditional on the true state, and the state of nature P remains time invariant. Okay. So here we denote by the small ht particular history of length t. And given a history, one can calculate the empirical frequency or simply frequency associated with this history, which is denoted by theta ht. And this is simply the number of outcome U's observed divided by the total number of observations t. Okay, and a set of length t histories is denoted by capital HT. And we denote by this curly HT as the set of all length t histories. Notice that a history here has two functions. First, it allows the decision maker to update his knowledge about this unknown state P. And second, it determines the payoff, okay? So these are the two functions of history. So first, let's look at the well-known first-order stochastic dominance and examine its implications in the binomial tree model. And the first-order stochastic dominance is perhaps the best-known stochastic dominance relations and is widely applied in economics. So the definition is, I believe, is well-known. So we say that F first order stochastically dominates G if the CDF at every point is greater under G than under F. A nice thing about first order stochastic dominance is that it has a very nice equivalence condition expressed in terms of expectations. So if if F first order stochastic dominates G, if and only if take any increasing function U, of course, U has to be measurable with respect to F and G. Okay, the expected value of U under F is greater than the expected value of U under G. So if you think about U as the increasing as a payoff function of a decision maker, then this condition says that every decision maker who prefer more to less will attach higher expected value under a first order stochastically dominating prior. This condition is quite useful, and this is one reason why first order stochastic dominance is so and notice that here in the tree model for any period t, F and similarly G will induce a probability distribution over the t+1 empirical frequencies via the following formula. So before we look at the formula, perhaps the following figure will illustrate the idea better. So this is a standard tree model. Okay, so here there are five periods. In period 5, there are 6 different nodes. For instance, if you look at the third node from the bottom, so this, so there are 10 histories leads to this point. Okay, so all points or all histories have the same empirical frequency 0.4. Okay, so if we are given a particular prior, one can calculate the probability of observing a history at each node in period 5. Okay, so therefore we obtain a probability distribution over these period 5 frequencies. So that's what we do here. So in the parentheses, so inside here, this expression is simply the probability of observing a history with empirical frequency k over t when the true state is p. But the decision maker does not know p, and then you simply take expectation, and then you get this probability here. So now the question we ask is, what is the implication of first order stochastic dominance in terms of this probability distributions over these nodes or empirical frequencies? So here is our result. Consider two prior beliefs F and G about the state of nature P. Okay, so F first order stochastically dominates G if and only if take any period T. Okay, then the probability distributions over the t+1 empirical frequencies under F first order stochastically dominates that under G. Okay, so this is the main result for first order stochastic dominance. But notice that it is well known that first order stochastic dominance is not preserved under conditioning. It means that firstly, if we take a subset of the support, let's say D, okay, suppose that F and D both have positive measures on D, and then restricted to this set D, F does not necessarily first order stochastically dominates G restricted to the same set. Okay, so if we think about a particular history, then the posterior beliefs does not necessarily preserve first order stochastic dominance. And the same also holds true for a subset of histories. So these are not really good properties because, you know, it's a first order stochastic dominance, although it is a very nice property, but it is does not survive any conditioning. Okay. So that's the problem with first order stochastic dominance. And it's not surprising because it is it's very weak notion of stochastic dominance. And so what is the, sometimes it is useful to look at probability distributions over subsets of histories instead of instead of these knots separately. Okay, for instance, here in period 5, one can think of the following partition: A1, A2, and A3. We can ask what is the probability distribution over this set of over these atoms. So naturally, the theorem 1 generates the following corollary. So consider any such partition PT of all the histories of the same length T. Okay, and for such that for any history in an atom with higher index, the empirical frequency is greater. Then F first order stochastically dominates G if and only if for any such partition, the probability distribution over the atoms of P under F first order stochastically dominates that under G. So this is a natural corollary, and it follows directly from the theorem 1. But sometimes it, yes.
I'm sorry for cutting you in. Is it okay if I ask a question now?
Yeah, sure, of course.
I actually have a question about it's the terminology, but also about the picture. So I think I understand the picture that you did. So in your terminology, these 5 nodes that are depicted, or 6 nodes that are depicted in blue here, are these histories?
These are not these are not histories.
Okay.
But these each knot corresponds. For instance, the second knot from the top, there are 5 different histories lead to this knot.
Yeah. Okay.
So yeah, but yeah. Thanks for clarifying this.
Yes.
Yeah, they just correspond to different empirical frequencies.
Yeah. Okay. Very good. Thank you.
Okay. So let me continue. So yeah. So this is basically the results for first order stochastic dominance. So we look at its implication for option valuation. First, European options. So what is a European option? A European call option or put option gives its holder the right, but not obligation to buy or sell a unit of certain asset for a certain price, referred to as the strike price, at a specific future date, which is referred to as the expiration date. Okay, so notice that you can only choose to exercise or not at the expiration date, not before. So everything here is fixed, the expiration date, strike price, and the asset price is given by this function, which depend on the location of the tree, okay, or it more precisely depends on the empirical frequencies. Okay, assume that the asset price is in great monotone in K. So the if the empirical frequency is higher, then the payoff is higher, or the asset price is higher. So the termination payoff for call option is maximum of these 2 items. Okay. So notice that traditionally, the option pricing focuses on the no arbitrage approach, namely that one can construct a portfolio using existing assets that exactly replicate the price movement of the underlying asset under consideration. So the equilibrium option price must prevent any arbitrage opportunity, because the portfolio exactly mimics the price movement of the underlying asset. So the prior belief, the belief of whether the next period you will observe an up or down outcome does not really play a role here, right? So that's the problem with the no arbitrage approach. And here we focus on the so-called subjective option valuation. So suppose that one cannot exactly replicate the price movement of the underlying asset. For instance, the market is incomplete. There are such as, for instance, there are many real options where the underlying assets are not financial assets, but some tangible assets, like the opportunity to make a certain investment, or the opportunity to use a certain piece of land for a particular purpose within a certain period of time. So these kind of options are referred to as real options. And very often you cannot find a portfolio that exactly replicate the price movement. Therefore, in such situations, prior beliefs becomes a crucial part of the option valuation. And that's our focus here, because we want to highlight the impact of different prior beliefs. So let's look at what we can do with the first order stochastic dominance. So
yeah. Can you say a few words about what all this means? So my understanding of the asset pricing was that this was a reflection of the belief about the state of the world. So
yes.
The more ups you see, then the higher is your posterior belief that the state is good.
Yes.
And now we are talking about some other beliefs. So what beliefs do you have in mind in the last part of the slide?
So here we're talking...
why would the price move for any other reason than updating your beliefs after K observations?
So here, to be more precise, we're looking at ex-ante valuation of an option. Okay, so let's say we're right at the beginning of this tree, let's say here. Okay, suppose for an European option, you can hold it for a fixed time, period of time, let's say period 5, in 5 periods, and then you decide whether to exercise it or not. And because at period 0, different decision makers, let's say, they hold different prior beliefs. One belief first order stochastically dominating another belief. Okay, so we want to examine the value that different decision makers have at period 0 about the value of the same option. Okay, so that's
how is the asset value determined if there are different beliefs about P? What is the meaning of the price? Who determines the price?
Are you referring to this asset price?
Yes.
This here?
Yeah.
This is known. Is given exogenously, assume. It is assumption. Is that okay?
Yeah, I guess so.
Yeah. So it fixes some price functions, okay? But maybe we can also allow for uncertainty in the price. I mean, if you move, the price can either move up or down. But when it moves up, you don't know exactly how much it moves up. Maybe it moves up by, let's say, 1%, or maybe moves up by 5%. You can, the asset price may subject to this kind of exogenous uncertainty. Okay. So
just last one question. Yeah. K is the period or is that
sorry,
a reflection of the
this k, small k here is the number of ups you observe, okay, and capital T is the expiration date or the total duration of this option. So suppose that because here for a European option, we only care about the last period. So by the last period T here, if you observe K ups, then your payoff would be given by this function S of K capital T. Is that does that answer the question or clarifying? Yes. Okay, so so actually the following result follows immediately from theorem 1. So for two prior beliefs F and G about the state of nature P, F first order stochastically dominates G if and only if the ex ante value of every European call option is greater under F than under G. Okay, so and similarly for the second part is completely analogous. So here that's the for all we have for first order stochastic dominance. And this is kind of a warm up. So, but we know that first order stochastic dominance is a weak one, and we can strengthen it by considering, for instance, the hazard rate dominance and reverse hazard rate dominance. We know that by definition, F reverse hazard rate dominates G if the following holds. Okay, and F hazard rate dominates G if this expression holds. Notice that here F and G are radon-Nicodean derivatives with respect to some common measure, which is not necessarily the Lebesgue measure. As a result, there can be atoms in the distribution. So it captures really very general situations. Okay, but notice that to check for hazard rate dominance and reverse hazard rate dominance, one needs to calculate the radon-Nicodean derivatives first, which may not be so convenient in particular when there are atoms. Okay, so we find that the alternative definition very useful, and these are, by the way, very well known in the literature. So F reverse hazard rate dominance G if and only if take any pH greater than PL, the ratio of the CDFs measured at pH is greater than the ratio of PDF measured at PL. And for a hazard rate dominance, we have a similar definition in terms of survival functions. So the following figure illustrates the graphical property of these alternative definitions in terms of CDFs. Okay, so let's consider a transformation phi that maps from the unit interval to itself such that F equals the phi of G. For instance, let's take a look at the panel on the left. On the vertical and horizontal axis, we plot the values of F and G respectively. And for instance, if at a value at a PL, GPL equals this constant G0 here. Well, FPL is this number. So the function, the transformation phi maps G0 to this level. So we have this point A on the graph of phi. So similarly, for a higher value pH, pH is still the same thing, but we see that FPH is higher. So therefore, the transformation phi is correspondence in general. Okay, so what these definitions for reverse hazard rate dominance says is that if we connect a point, let's say A here on the graph of phi to the origin, okay, then the slope of this line segment will gradually increase as we move the point to the right. In other words, imagine that you are standing at any point on this red curve or this transformation. Then at any point you can observe the origin, okay? Or if you put a light bulb at the origin, the light can reach any point on this phi function. So that's a nice graphical property. reverse hazard rate dominance. For hazard rate dominance, we have something similar, but it's with respect to the other extreme point, 1, 1. Okay, so if you put a light bulb at 1, 1, then its light can reach every point on this transformation. That's the graphical property here. And this graph, using this equivalence condition in terms of CDF, one can derive the following equivalence condition phrased in terms of expectations. Okay, so this equivalence condition says that F reverse hazard rate dominates G if and only if the following inequality hold. And this expression, it could be more useful, but of course the denominators have to be non-negative. For all function U and V such that the expectation exists and V is non-negative and increasing, and U is increasing. Okay, here by increasing, decreasing, we mean weakly increasing or decreasing. One way to understand this equivalence condition is the following. For any V which is non-negative and decreasing, we can define a new CDF F hat as the following. Essentially, this is just a change of measure, okay? So then the equivalent condition simply says that under this transformed CDF, F hat first order stochastically dominates G hat, okay? So this condition is actually very useful because because the posterior beliefs conditional on certain set of histories or can be written in this form like this, right? As you will see. So it allows us to derive some results related to posterior beliefs. And analogously, we have a similar result for hazard rate dominance. This is the equivalence condition. Notice that the difference here is this V function, which is assumed to be non-negative and increasing, while for reverse hazard rate dominance, it's decreasing. Okay, so the rest of the things are the same. Using these equivalence conditions, we can derive the following result of reverse hazard rate dominance in the tree model. So suppose F and G are non-degenerate at 0 or 1. It means that F and G do not put all probability mass to either 0 or 1. In other words, it implies that each history can be observed with positive probability. Okay, so if you make such assumption, then the following conditions are equivalent. First, F reverse hazard rate dominates G, and second, for any period T, and take any threshold theta between 0 and 1, and define a set of history capital HT minus as the collection of all histories of length T, such that the empirical frequencies is less than this given threshold theta. Okay, so then the posterior beliefs conditional on this set of histories preserves hazard rate dominance relation. That's the second condition. In a sense, the first and second equivalence of first to second condition says that reverse hazard rate dominance can be preserved under conditioning. This is already by contrast to the first order stochastic dominance. And the third condition is slightly weaker. It says that for the same set of history considered in 2, F conditional on this set, first order stochastically dominates G conditional on this set. So we show that under a weaker condition, namely 3, it is already enough to guarantee F reverse hazard rate dominates G. And the fourth condition says that consider the same set as in 2 and 3, the probability distribution over this set of histories induced by F first order stochastically dominates the probability distribution over this set induced by G. Okay, So 1, 2, 3 are in terms of priors and posteriors, and number 4 is in terms of probability distribution over a certain set of histories. So this figure illustrates the set under consideration better. So let's look at the panel on the left. So the set HT minus here corresponds to all histories that leads to these 3 knots at the bottom. Okay, so this is for reverse hazard rate dominance. You can of course imagine what happens for hazard rate dominance. The figure on the right already gives you some hint. Exactly, yeah.
So I'm sorry again. What's the difference between 3 and 4?
Okay, 3 is the posterior belief conditional on this set of history. Okay, so this is posterior belief. Okay, and 4 is the probability distribution over histories. For instance, look at the panel on the left, and there are 3 blue dots on the bottom, right? And each knot there's few histories that leads to this knot in period 5. Okay, then essentially what proposition 4 says is that we look at probability distribution over these 3 knots. Okay. So recall that for first order stochastic dominance, we look at the probability distribution over the entire over all the knots in period 5. Here we just look a subset, namely the knots at the bottom, and it says that if for any such set of histories, the probability distribution under F first order stochastically dominates the probability distribution over G, then one can guarantee that the F hazard rate dominates G. Does that answer your question?
Yeah, thank you. It was the notation.
Yeah, so it's, yeah, I should emphasize here, but they are talking about different stuff.
Yeah.
2 and 3 are in terms of posteriors, and number 4, like this graph is, we're essentially looking at probability over these blue dots. Okay, because essentially we want to evaluate the payoff. We want to calculate the expected payoff conditional on a set of histories. Okay, so that's the result for hazard rate dominance. For reverse hazard rate dominance, it's completely analogous. I believe you can already guess it. So the following conditions are equivalent. If everything remains unchanged, except that the histories under considerations are different. So here we consider histories on top of on the top, but for reverse hazard rate dominance, we consider histories at the bottom. Okay, so that's the difference. And essentially, hazard rate dominance and reverse hazard rate dominance, they preserve, they are preserved under conditioning for certain set of histories. So let me just give you a very brief sketch of a proof for several steps. To highlight, several equivalence conditions here. First, we show that F reverse hazard rate dominates G implies that the posteriors conditional on the set HT minus still preserve first order, reverse hazard rate dominance. So if notice that the posterior belief measured at a particular point P hat here can be written as follows according to the Bayes rule. Okay, notice that this B function is simply the probability of observing a set of history HT minus when the true state is P. And one can show that it is strictly decreasing in P. Namely that when P is higher, it is less likely to observe those histories at the bottom. Okay, that's the idea. So B is a non-negative and strictly decreasing function. Okay, and then it follows from the equivalence condition that this is we care. Okay, so the posterior belief, and we calculate the expected value of u times v over expected value of u using this posterior, and we want to show this is greater than this part. And then according to the equivalence condition we derived earlier for reverse hazard rate dominance, we can guarantee that this holds, right? But notice that using this expression here, one can write this expression as follows, and this v function is non-negative and decreasing, and b is non-negative and decreasing, so their product is non-negative and decreasing. So this inequality follows due to this assumption, right? And the equivalence condition we have here, right? So this is just to highlight the power of the equivalence condition I mentioned earlier. So for the another direction, we can show that f conditional on ht first orders. If this holds, then it is sufficient to guarantee f reverse hazard rate dominates g. For this, we have the following lemma. So let's consider this set as the set of all length t histories whose empirical frequencies is less than a threshold pH. Then we take any PL less than this threshold. As time goes to infinity, one can show that the posterior belief measured at this point PL converges to this ratio, and similarly under G. Okay, so this nice property allows us to derive a contradiction easily. Now suppose that F does not reverse hazard rate dominates G, then by the definition in terms of CDFs, we have this, okay? And then we let time t goes to infinity and consider this set of history, which it follows from the fact that the posterior first order stochastically dominates the posterior under G, that this ratio under G here is greater than this. So it leads to a contradiction. So essentially that's some part of the proof. So I'll, for the sake of time, I cannot cover all the details. So these are the key results for reverse hazard rate dominance and hazard rate dominance. So in terms of European options, theorem 3 and theorem 3 prime implies the following. So F hazard rate dominates G if and only if for every European call option, the option value conditional on the option is exercised is greater under F than under G. Okay, because for every European option, it is exercised only for histories above a certain threshold, like the figure on the right. Above some certain threshold, then you exercise. Below it, then you do not exercise, and you get zero payoff. So conditional on the option is exercised, namely we restrict our attention to the 4 blue knots, then we can calculate the conditional expected payoff. Then here is the result. It follows immediately from the previous theorem. Okay, so these are a slightly stronger notion of stochastic dominance. But of course, we know that there are even stronger notion of stochastic dominance, like the likelihood ratio dominance, which is used quite a lot in economics. And the definition is very well known. It says that F likelihood ratio dominates G if and only if the ratio of their densities is increasing in P. But of course, this F and G are Radon-Nikodym derivatives with respect to some dominating measure. So it also captures situations in which there are atoms. Okay, so analogous to the previous stochastic dominance relations, we can have definition in terms of CDF directly. So here is the definition, and you don't have to look at it because I'll show you a graph. It says much better than this. Okay. So here again we look at the transformations from G to F. Okay, and then we have some the red curve here. We call it phi. And what this alternative definition says is that the slope, take any point x1, greater than x2, greater than x3. What this definition says is that the slope of C and B is greater than the slope of A and B. Okay, in other words, if you draw such a transformation phi, then it means that phi is convex. Okay. Or in other words, if you put a light bulb at any point on the transformation, then the light can reach any other point on this red curve. So this is already much stronger than reverse hazard ray dominance and hazard ray dominance, in which you can only observe the two extreme points. Okay, here you can observe any other point. So for likelihood ratio dominance, it's interesting that we have a completely analogous equivalence condition expressed in terms of expectations. Notice that here, this V function is only assumed to be non-negative. Okay, recall that for reverse hazard ray dominance, this U function that appear here is assumed to be non-negative and decreasing. For hazard ray dominance, this U is increasing. Here, for likelihood ratio dominance, we do not impose any restriction other than non-activity and measurability, of course. And this, sorry, we're talking about V function. So I just, and this U is increasing, okay? And again, one can think in terms of change of measure as before. So using this equivalence condition, one can derive some analogous result here. For the tree model, suppose F and G are non-degenerate at 0 or 1, then the following are equivalent. The first one is likelihood ratio dominance of prior belief. And second one, you take any history of length t. Okay, it does not necessarily have to be on the top or on the bottom. It has just to take any such set of length t histories. The only requirement is that the histories in the set must be of the same length. And then conditional on this set of histories, the posterior under F likelihood ratio dominates that under G. In other words, likelihood ratio dominance relation is preserved under conditioning for any such set of histories. This is a very nice property because it, you know, you can basically consider any set of history that interests you, okay? And then the posterior still preserve a likelihood ratio dominance. And we can consider also the weaker condition, namely the first order stochastic dominance of the posterior. And under this weaker notion, this weaker condition, one can guarantee the first condition. Okay, and the 4 is also analogous for any such set HT. The probability distribution over the set of histories induced by F first order stochastically dominates that induced by G. So for instance, the following graph illustrates the set of histories under consideration. It might be all the histories that leads to the 3 dots in the middle, or you can take 1 dot from each box on the right and form a set of histories. All of these are allowed. Okay, so you can see that it covers a much wider range of histories. So for option valuation, we find that likelihood ratio dominance is related to American options. Unlike European options, where you can only hold it to the termination date and do nothing before it. For American options, you enjoy the flexibility of early exercise. Basically, you can exercise at any time before or at the expiration date. Okay. Notice that here the asset price evolves according to this function, SKT. T is a particular period, and T is the number of use that you observe. And the payoff for American call option is simply the following. And this T here, it should be the stopping time. Okay, whenever you stop and you look at the asset price when you stop and minus the strike price. Essentially, for American options, the decision maker faces an optimal stopping problem. So SKT minus S bar is the payoff when stopping immediately, and the remaining part is the continuation payoff. So suppose that in period T, we're at position KT, and next period, with some probability, you'll receive a new outcome, and therefore you have a value function at the node KT plus K plus 1 T plus 1, and with the remaining probability, you are at the node KT plus 1. Okay, so that's the continuation payoff. So what we have for American option, the first result is that suppose F and G are not degenerate at 0 or 1, and F likelihood ratio dominates G, then the value at every node, or conditional on each history, the option value is greater under F than under G. Okay, this is not surprising, because our result implies that at any period, conditional on any history, the probability you observe an up outcome next period is higher under a likelihood ratio dominating prior. Okay, so because this is this part. Okay, so likelihood ratio dominance is preserved under conditioning. In particular, it preserved under conditional on a single history. And second result says that suppose F and G are not degenerate at 0 or 1, and F likelihood ratio dominates G, then for every American option, whenever it is optimal to exercise under F, it is also optimal to exercise under G. Okay, so in other words, for every American option, a decision maker with a likelihood ratio dominating prior tends to wait longer. Okay, so so this is the meaning of proposition 2.
And this
so
is
we know that, yeah,
this is presumably true for any discount factor, delta between 0 and 1?
For any discount factor. But of course, fix a discount factor and fix American option. Whenever it is optimal to exercise under F, it is optimal to exercise under G. Is that, Igal, is that what you're asking?
Yes.
Okay, great. So here, the delta is treated as fixed. Okay, so but we know that typically, talking about patients, okay, we know that people with a higher discount factor tend to be more patient because they discount the future less, right? And here, the interesting observation is that the likelihood ratio dominance relation among prior beliefs can also is also related to patience in a sense, because here, according to proposition 2, if your prior belief is a likelihood ratio dominating, then you tend to, whenever it is optimal to exercise under F, you know, whenever it is optimal to wait under F, under G, it is optimal to wait under F. Okay, so that's the message that proposition 2 tries to convey. About the valuation of options, actually, we can generalize proposition 1 further. So for proposition 1, it's the value conditional on each single history. We can look at the value conditional on a set of histories. That's what we have for theorem 6. So if we consider F likelihood ratio dominates G, then this is equivalent to, for every American option and every set of history HT, such that the option is not exercised, conditional on the option is not exercised, okay, then the expected option value conditional on this set HT is greater under F than under G. It's a slightly, it is a slight generalization of proposition 1. Okay, so of course you can already see that here the results are richer because essentially the likelihood ratio dominance allows us to, is preserved under conditioning for a fairly large class of histories. Okay. So finally, we are looking, we look at the case in which the prior is fixed, but the histories are different. So we will see what happens. So proposition 3 says the following: consider two different histories, let's say HT and HT prime. They have, of course, they have to be of the same length. If HT has more observations of outcome U, then for any prior FP, it could have atoms or any number of atoms as you like. So it's kind of very general, okay? Then the posteriors conditional on this history with higher empirical frequency, first order stochastic dominates the posterior conditional on the history with lower empirical frequency. That's this result. So you start from the same prior, but different beliefs, different history will lead to different beliefs. And it turns out that there is a nice first order stochastic dominance among posteriors here. Okay, sometimes you can also look at posterior conditional on a set of histories. So here is the corollary of proposition 3. So if you look at two sets of histories, HT and HT prime, suppose the frequency of any history in HT is no less than the frequency of any history in HT prime, then still you have this first order stochastic dominance relation of posteriors. But notice that here in proposition 3, the two histories must have the same length. If we consider histories with different lengths, then this result may not hold. Okay, so you can think about an extreme case in which HT, one history just has one observation, which is an up. Okay, so then for this history, the empirical frequency is 1. You can think about another history that has a that is very long. Okay, because by the law of large number, conditional on this long history, the posterior is concentrated at a certain point. Okay, so you can, in such a situation, the posteriors does not satisfy this first order stochastic dominance, despite one has higher empirical frequency. So that's something we have to mention about proposition 3. So essentially, that's all we have in this paper. So yeah, essentially that's just this remark. I think I covered it. So I think I have 1 hour, right? So let me conclude. Basically, in this paper, we analyze the implications of several different stochastic dominance relations among priors in the binomial tree model. which is used a lot in economics. We covered the following stochastic dominance relation: first order stochastic dominance, reverse hazard rate dominance, and hazard rate dominance. And these two are not, to the best of our knowledge, we do not see a lot of applications of these two stochastic dominance. But here we see that there are some nice results about them, and the likelihood ratio dominance. And it's interesting to observe that these several stochastic dominance relations are closely related to each other. Okay, so for many equivalence conditions we derive, they are kind of parallel, but each imposes extra conditions or extra requirements. So for each stochastic dominance relation among priors, we investigated stochastic dominance relation of posteriors, and we also examined the probability distribution over a certain set of histories, and we demonstrated that this is could be useful to evaluate, let's say, the options, right? And as an application, we studied the implication of these stochastic dominance relations in subjective option valuation. Basically, that's all the results I would like to present here. So if you have any question or remark, I will be very thankful.
So thank you. Thank you, Tal.
Yeah, thanks.
And now, of course, if there are any questions, please, people, feel free. You can just unmute yourself and ask.
Sorry. Oh, okay. Yeah. So thanks everyone for coming to this talk. We can. Yeah.
Wait.
Yeah.
I already asked many. I was quiet because I already asked many questions. So
yeah.
It would be okay if I ask yet another.
No problem.
Okay. So is it correct that LR implies both HR and RHR?
Yeah, sure.
And
it's the strongest
converse.
of all of them.
If F both hazard rate and reverse hazard rate dominates J, would it also dominated according to the likelihood?
No. This is yeah. The answer is no. It's quite clear because recall that where is the graph? Okay, let me. Yeah, where is it? Just because if you recall, yeah, here, look at this graph. For reverse hazard rate dominance, at any point on this transformation, you can only see the origin. For hazard rate dominance, you can only see the other extreme point, 1, 1, but not necessarily any other point in between, right? But for likelihood ratio dominance, each point can see any other point. So that's much stronger. But for reverse hazard rate dominance and hazard rate dominance, you can only see one extreme point. So and actually there are you can draw figures, but I don't have it here. But you can draw figures like this and show that there are cases in which you can both see the origin and the extreme point 1, 1, but not necessarily any other point in middle. So there are counter examples like this. So it's the answer is quite clear. The reverse hazard rate dominance and hazard rate dominance, they are together. They do not imply likelihood ratio dominance. And you can also look at the history under consideration. For hazard rate dominance, notice that we consider all those histories at the top. For reverse hazard rate dominance, it's only those history at the bottom. Okay. So for likelihood ratio dominance, it's much richer. It can be anything with the same length. So it's much richer. yeah. So, does that answer the question?
Yes, absolutely. Thanks. It just reveals my lack of knowledge of these two.
Yeah, it's this I should also mention that yeah, it's interesting. This is a very nice question.
It's interesting that you did not talk about second order stochastic dominance, because that's also very often used in.
Yeah, exactly. There are actually a lot of work on the second order stochastic dominance. There are a lot of work have been done in that area. As I mentioned, that the second order stochastic dominance and third order stochastic dominance, these are related to the dispersion or variation of random variables. Here, the likelihood ratio dominance and the rest we're talking about, they are related to the location. Okay, so they are different aspects of stochastic dominance. Yeah, but you're definitely right. There are a lot of work has been done on about the risk attitude, the second degree, third degree. Yeah, for that we have nothing more to say.
Is there a characterization of LR that does not involve the densities, like there is one for the other two?
Not including densities, right?
Yes, not the derivatives, but the distribution functions themselves.
Yeah. As I talked, yeah, just I have here. Just a second. Where is it? Here. This alternative definition. This is in terms of CDFs. So yeah, this is the nice thing about this definition is that it only involves the CDFs. It's more direct, and it has this nice graphical property. So the transformation is convex. Okay, so yeah, that's yeah. Any other questions?
Okay, then we thank Tao again.
Okay.
Thank you.
Thank you for the questions and for coming to the talk. Yeah, if you have